Okay, hello and welcome to this session on circuit theory, hosted by Brunel Robotics Engineering Society and myself, Ben Mounier. So, what are we actually going to be covering in this session? The learning objective is to get you guys familiar with basic electronics and how a few components work, what they look like, and their general applications. So we'll be going through the kind of general principles, and this will be a very kind of PowerPoint-based start, bit like a lecture, I'm afraid, to understand the concepts. Then we'll be going through some of the components, and we'll be doing a bit of practical study in between to show you what those kind of do. Again, this is not a certified course. I'm not an expert, and please always be careful with electronics. This is just a helpful guide of what we think might be useful for you to know. Please also do refer to as many additional resources as you can. There's so much on YouTube. This is just a general overview. I will be trying to link as much in as I possibly can. Okay, so I will ask you to bear with us. This first bit is a lot of information to take on. This session is quite dense, but we've tried to make it as enjoyable as possible, but you kind of need to know it. Understanding this stuff is essential. This is the basics of circuit stuff. And if you want to make cool things like that little robot arm on the right, it's good to know all of this, okay? On Thursday's session, we'll be assembling your own circuits, virtually of course, but this is important. This is the foundation understanding so that you understand what's going on Thursday. And there you can see one of the circuits in the top right. This is kind of what we'll be developing on Thursday. It might look a bit complicated now to some of you. Again, this is the basics and essentials. So for some of you, this might be very, very new, and I will try and make it as easy to understand as possible. For some of you, this might be very kind of stuff you've learned years ago, and this might be fairly basic. So bear with us, and you know we'll try and make it over for everyone. Again, if you want to make cool things like that, then you need to understand this stuff. It's very simple. Okay, so starting with the very, very basics, current theory. Okay, what is current? Current is the flow of electrons. Okay, for those that don't know. Electrons are subatomic particles found surrounding nucleuses of all particles, okay, and we measure current in amperes or amps. Okay, so here you can see the positive and the negative terminals, and these are all the kind of particles within a material, and you can see the electrons here surrounding the nucleus being shared, and so this here is the flow of electrons. Yeah, we can see it from the negative side flowing over to the positive side. Okay, so they're attracted to the positive. Negative is attracted to positive. We know this. So electrons flow through conductive materials like metal. Hence, we use wires, obviously, to transmit electricity. I will say that some of this might seem rather, primitive, rather basic, but you have to understand it, and it's out there for everyone. So I'm just covering all levels. So we have a complete circuit, and we call that closed loop. Which means that basically the current can't flow if there's nowhere to go, and so we call this this is a closed loop. So there is somewhere for the current to go, and you can see a pump is pushing water around, and this is a great analogy of using water. So if you consider electrons like the water molecules in a pipe, if we then go cut that pipe, so we separate it, we call this open loop because we've opened the loop up and the current won't flow, the water won't flow through. Okay, so water is quite a good analogy that I'll be trying to maintain through this presentation about current. Okay, so this is now open loop, and before we had closed loop. Okay, so current theories, supplies. Now you see two circuit symbols as well here. We have alternating current, which is kind of what you might get in a house socket. This is what you find in a household socket. And you've got direct current, DC, okay, which is very kind of common battery stuff that you'll find lying around that you plug into the back of remotes and stuff. So alternating current periodically changes. It's constantly alternating the flow of electrons, okay, and this frequency of these changes is measured in hertz, which is your cycles per second. And here, you can see this GIF, you've got a supply, this using this circuit symbol, and here you can see the flow of electrons moving one way and then changing and going the other way. So this is what we call alternating. This is used for long distance transmission, given the ability to be stepped down very, very easily, or stepped up, which is basically increasing voltage or decreasing voltage, and current vice versa. So direct current, on the other hand, has a constant flow of electrons. When I say that, it has a constant direction. Okay, so here you can see DC, you've got your DC power supply, positive and negative, and it's always flowing this way. Okay. And this is used in most common electronics, your batteries, your phones, the computers you're on now, and everything we do pretty much at a hobby level will mainly be DC. Very, very few cases of AC. And here you can see the current flow. So over time, your DC current is always positive. Here it's going positive and negative. Okay, it's always changing direction. It cycles over like this. So current flow. Now, you might have picked up that actually in the two animations, you've seen the flow of current in different directions. That's because there's a thing called conventional current, which is where we always assume things go from positive to negative, and it's a very conventional method, versus the actual electron flow. Electrons always flow from negative areas. So here you can see the blue electrons flowing from the negative to the positive, okay? And essentially here, this battery has two areas. We've pulled them apart, essentially. We've divided a low density area of electrons and a very high density area of electrons, okay? And basically, once we connect them up with this wire, the electrons are free to move through, and they will transfer through this wire, as we saw before. They'll bounce across all of the molecules, and they'll flow from the negative area to the positive area. And this is done because electrons all want to reach equilibrium, very common in nature, even throughout. So they will keep moving until they're balanced out. And they will keep doing this because we've created an imbalance, okay? And we've created this high and low area. This imbalance is what we call potential difference. And the greater this difference is, the greater this imbalance is in electron density, greater the potential difference. And this potential difference is what we call voltage, which is your driving force, which pushes your electrons. Okay, so potential difference, or voltage, is measured in volts and essentially forces the electrons around the circuit. Okay, the greater this potential difference, the more force these electrons have. So here, if you imagine this water in a tank is going to flow out a lot faster because it's got a lot more energy. It's got all this water pushing down on it. Whereas here, there's not a lot of force. Okay, so lower potential, lower voltage, less force. Okay, again, this water analogy, current is now the flow of water through the pipes. So more current is more water flowing through if you chopped it in half, you took a cross section at one point. Whereas voltage is the pump, or perhaps a tank, forcing the water around. It's the pressure of that water. Okay, so more voltage means a stronger pump and more force. Now resistance in ohms. Everything has a bit of resistance. And this is a man here, lovely Mr. Ohms, came up with this. Well, not came up with it, it's physics. But he decided and figured it out. So resistance, usually provided by a resistor, which is this squiggly little line, and we'll be covering a little bit more of later, reduces the flow of current. It provides resistance to the flow of current, right? You can think of it like a narrow pipe, a narrow piece of the pipe that slows down how much water can go through. It reduces the amount of water that can actually go through, okay? And Ohm's law came up with a relationship between voltage, current, which is denoted by I, and resistance, which is R. Voltage is equal to current times resistance. And I'm not kidding when I tell you that this is the most important equation you'll need to know, okay? And one thing to also note is that electricity will always choose the path of least resistance. I think that's true for probably most of us. It'll choose the easiest route, okay? Now, this is a very, very important piece of information. Now, we're going to cover this as quickly as possible, and then we'll get onto the fun stuff, believe me. But essentially, there are two kind of ways that you can lay out components to one another in relation to one another. In series, where a component is one after another. Here we have a lamp is then connected to another lamp, and they're connected in series. You pass through one and then the other, or in parallel. And here, essentially, you reach the current would find a fork in the road, and it would have to go into these two things at once, at parallel, and then connects back up and flows back round, right? So we just think of this. It's kind of like connect the dots. So in series, current is exactly the same throughout all of the components. These are the kind of rules you need to know. Current throughout these two components is exactly the same. However, the voltage is divided between the two of these. Okay, the voltage between both of these is the same as the source voltage. In parallel, however, it's the opposite way around. Current splits, so the current at this fork is suddenly going to split, and not evenly all the time unless they're identical. Current will split at this point, whereas the voltage in both of these lamps will be exactly the same. Okay, and I'm going to help you out understanding this. So in series, our current is the same throughout all. So here we have our supply current, right? So this is the current that we have at the battery. These two are going to use it up. So we've got our current here in between, our current here after the lamp, and the current here. And I can tell you that the supply current is exactly the same as all of these other currents. The current here is always even. Okay, it's always balanced. However, the voltage of the supply and the voltage through this lamp and the voltage through this lamp are summated like so. So you have the voltage of the supply is equal to the V1 plus V2. In parallel, as we know, it's the opposite way around. So as you can see, the current at these points, I2 and I1, where it splits up, these will add together to create or to be your source current. Okay, and then when they join back up this node, when I2 reaches all the way around, meets I1, and they form together to make I3, right? So they join together. Whereas V1 and V2 through these two channels here, these parallel channels, are equal to each other. Okay, there's no difference to them, and this will gradually become clearer. Okay, so using these rules, we can now understand how to measure our current, and we use an ammeter. So this little device here with an A, very simply labeled, and we know that current is equal in series, right? Therefore, we're going to put our ammeter in series to figure out, right? We know that the current at this point is the same at this point, is the same at this point. So therefore, using this rule, we're going to put our ammeter in series, it doesn't matter where, and we're going to find out the current going through. Now for voltage, we use a voltmeter, very, very cleverly named, I know. And we know that voltage, if we look at our laws again, is equal in parallel, right? So if we're trying to find our voltage across a component, let's say this lamp here, we're going to have to find the voltage, not by putting it in series, but by putting it in parallel. So let's go ahead and do that. So we go ahead and put this voltmeter in parallel with this one, and now we know that the voltage going through the voltmeter is the same as the voltage going through the bulb. We also then, if we wanted to figure out the voltage going through this lamp, because we know these two lamps aren't going to have the same voltage in series, we put the voltmeter across this in parallel, and we now know that the voltage going across this is the same as the voltage going through our voltmeter, and we're going to get our voltmeter reading. Okay. Now, like here, we've had to add 2 voltmeters because we want to measure the component, both the component voltages. Now, because it's very uncommon to have a voltmeter and ammeter lying around, we use very aptly named multimeter, which can be used as both the ammeter and the voltmeter. You just need to change the dial on this setting. So we can put it exactly where we had all our voltmeters and ammeters before, just change the settings. Now, measuring resistance. Very important, we come back to Ohm's law. Measuring resistance in series is very, very simple. If we've got these 2 resistors here, all we need to do is add them up. So R1 plus R2 would be exactly the same as if we had this one resistor. It would make no difference. The resistance across these is going to be exactly the same as the resistance across one. That's the summation of these 2. Measuring resistance in parallel, though, however, has a little bit more of a jazzy kind of calculation. We have to add the inverse. So 1 over R total is equal to 1 over R1 plus 1 over R2. I could go into all the details behind this, and I really suggest you do look at it, but I'm trying to gloss over a few things. If you are interested, I can send some more resources about this, but essentially this circuit here would be exactly the same as these 2. You would join these 2 up using this, and 1 over R total would be essentially this equation, and you just figure them out. And so these 2 are exactly the same. Okay, so this circuit is now the same as that one or that one. So let's try and visually understand some of these concepts, okay? Firstly, DC power supplies, okay? So as we've said before, like your little battery sets that you've got, they come in all types, shapes, and sizes. Here we have a lithium polymer, and here we have a car battery, and essentially it's the chemical mix-ups, it's the sizes of them, it's lots of things that can change it, and they all have varied output current and voltages, right? They all will output something a little bit different, hopefully not between the same types, obviously. The main thing to note is that batteries will have a positive and a negative end, right? That's where you're going to connect. That's where the potential difference is. And one jazzy thing, it's not really interesting to know because everyone's going to call it a battery. We all call this a battery, but technically it's a cell, because a single cell is a cell. Two cells make up a battery, or multiple cells make up a battery, okay? But don't be that guy. One other thing we can do is, now that we know about series and parallel, obviously, we can connect batteries up to change the output current or the output voltage. So here we have two batteries that are 6 volts each. If we connect them in series, so we connect negative of this one to, no, going to go to the positive, which is going to go to the negative of that one, and then we go through again. Make sure you're connecting positive to negative here, so it bounces all the way through. We're going to get 12 volts. This is going to add in series. Our voltage adds in series. Remember, our output voltage is going to be the summation of these two. Whereas if we connect them in parallel, where we put positive to positive and negative to negative, the current's flowing through these two. Our voltage is the same this time, but our current has doubled. Okay, the current has doubled because in parallel our current's doubled. Okay, so this is useful if you want to increase the current or the voltage of your supply. You can join them. Here we've got them in series, so we've got negative to positive, positive to negative, and then negative to positive. Do not, and I'm going to make this very clear, do not connect batteries of different voltages together like this, okay? Consider the fact that they will want to reach equilibrium. So the bigger battery, say this was 12 volts, will want to charge up the smaller battery. That's going to try and reach equilibrium, right? So this is going to try and reach a balance all the way throughout. It's going to try and charge up your smaller battery. Your smaller battery is not made to reach that voltage level, and you could push it beyond its capacity and boom, something goes wrong, nobody's happy with you, and you could seriously injure yourself. So do not connect batteries of different voltages together like this. Okay, so looking at batteries, we have the common AA battery, which you might recognize, which has a 1.5 volt rating. So we have the common household AA, which has a negative and a positive end, as you can see. We then get on to what you might recognize as a PPE, or a 9 volt battery. So there it says 9 volts across it, with both a positive terminal, so you can see positive on that side there, and negative on that side. So you got your PP3. We then have some LiPos, as this is a 12 volt battery that you can see here, and it's rather large, and that has a different connector on the end, but also has a positive and negative, as well as a smaller LiPo battery. This one's used for a drone, and this one has a very clearly marked positive and negative with a different connector, positive being the red one and negative being the black, obviously. So we also have what I should be calling a cell here, a single cell, and if we join it into this housing here and slot it in like so, we've now created a battery where we have these two in series. So it's very similar to this symbol here now. We've connected the negative end to the negative end of this black lead, which is always color coordinated. And then we have the positive end connected to the negative, and the positive end of that connected out to this positive red lead. So that's kind of everything you need to know about batteries. They're kind of useless on their own, but if we mix them with some stuff, it should get more exciting. Light-emitting diodes, however, are a little bit more exciting. Light-emitting diodes emit light very basically when current flows through them. Okay, and here's a circuit symbol for them, and they've got two little arrows that basically highlight the fact that light's going to emit from them. And this is what they look like. I'm going to show you them in a little bit. What's important to note is that they have a polarization, okay, meaning they only work in one way, right? Current here, I, is only going to flow through it this way, the way the arrow points. They've cleverly given you an arrow indication for which way the current flows, okay? And this stop line here, this is pretty clearly that it doesn't want to go through the other way. So it has a positive end, and we're going to put the positive end through that way, and a negative side. Now the positive end is what we call an anode, right? And this is highlighted on a lot of components by a longer leg, okay? So the longer leg is the positive one, or the one that you connect to the positive side, and the cathode is your negative side. On an LED will have a flat edge, and I'll highlight that in just. Okay, so LEDs come in a variety of colors, shapes, and sizes. But what's important to note is that here we have the positive and the positive longer anode and the shorter negative cathode, which are both of these legs. We can bend our legs out, we can separate them slightly, and then we take in our 3-volt power supply, which is our two AA batteries in that configuration. And we take our black lead and connect it to the shorter leg, and we take our positive lead and connect it to our longer leg, our anode, and we see that we light up the LED. Now I'm turning it off simply by disconnecting the cable, breaking the circuit, stopping the current flowing through. We're just opening that loop. Okay, just to reiterate the point we made, if I turn it all the way around, put the negative now to connect it to the longer anode and touch, make the loop again, and nothing happens. Now, one important thing to note is we did that with these two AA batteries. If I go ahead and take the 9-volt battery, and I want you to see this, if I connect this now across the two terminals, I'm not sure if you saw, but there was a burnout there. And that is because this voltage is far too high for this LED. This LED is now burnt out and won't light up again, no matter what we do. That is now good for the bin, that's gone to waste. So how do we prevent damaging components using too high voltages? We need to consider resistance, right? We need to limit the voltage. So if we want to use a higher power supply like that, we need to limit the current going through, right? Right now we think of wires, as we've seen before, having no resistance, and they pretty much do. Okay, and resistors look like this. They've got lots of colourful bands. And resistors are essentially made of a material that makes it harder for electrons to flow. Okay, they just limit the amount of current, they just resist it. They have no polarity, so you can put any one of these legs in either way, it doesn't matter. They do have a coloured band system, which helps you identify the amount of resistance that that resistor actually has. So these colours all identify the level of resistance of that resistor. And here you've got two different types of symbol. This shows exactly the same thing, just different standards. So you can draw it like this, or you can draw a square. Now we can add one to our circuit to prevent our LED from burning up. Okay. And if you want to go back to that water analogy, remember a resistor is like a narrow piece of pipe limiting the flow of water. So now if we add a resistor of the right resistance, we will prevent our LED from blowing up because we will limit the big current coming through. Okay, so let's take a look at that. Okay, so if you look in the bottom right corner, you'll see the circuit diagram that we're using here. And so you can follow along from the positive node of our battery along to our resistor, which is then connected to the long leg or the positive anode of our LED, and then that comes out to our negative leg. So now that we've applied a resistor, when we connect the battery up like so, we see that there is no burning of the LED. The LED now remains intact. This next demonstration, we have a variety of ranging resistor values. So this is 330 ohms, 1000 ohms or 1K, and 10K or 10,000 ohms. So if we connect up our positive of a smaller battery, we can see that here the 330 is fairly bright. The 1K is not so bright, and the 10K is barely on at all. If you can see that, it is lit, but there's no light. So the higher the resistance, the less current is flowing through, and therefore you can see the lights get dimmer. So, I don't know if you've noticed, but it's been quite fiddly stuff trying to wrap those resistors around. So what we do use are breadboards. Okay, breadboards are absolutely fantastic for providing an easy way to kind of put components together. And breadboards allow us to temporarily join our components together by containing these little, these strips. So we have to arrange our components like we do considering the connections of our circuits. We have to arrange them correctly. Okay, so breadboards are simply made of metal strips. Okay, so here you can see underneath you've got all these holes where you can put a component's leg through, right? And then you've got all of these metal strips that connect them up, right? And look at the pattern, paying attention to the pattern of this. Now, if we put our LED here, that's symbolized here, across these two paths, underneath here it's connected one of the legs to this rail, to this metal strip, and the other one to this metal strip. Okay. If we do it like this, this is all joined on one strip together, right? So that means that you've essentially managed to connect both the legs together, and it's done nothing. It's like tying the legs of a LED together isn't going to be great. Some variations of breadboards, so here you can see all the connections across here, across the short side, will have these longer ends, which are usually highlighted in red or blue. And they essentially have long metal strips. And this is usually where you connect your power supply to, like you connect your 5 volts and your 0 or ground to the blue. Okay, so essentially poking components legs through a hole connects that leg to anything else on the same metal strip. Okay, so looking at a breadboard, what we have here is what we saw before. All of our rails connecting like so along here, and then our long negative marked with the blue negative color, and our positive rails here, and this breaker in the middle, this divide across the middle. We can easily see this because I've ripped off the backing of this breadboard. I wouldn't recommend it. And here you can see all of the conductive strips. So all of the strips going down, none of them connecting across that middle bit, and then the conducting strips along this long edge as well. So if we now take a look at this little circuit I've prepared, which is similar to the one on the bottom right here, but first we're just using one LED. We can see, I'll connect that up there, we can see that we start here at our positive rail. So we've connected our positive into this rail, meaning all these points here along this entire thing are connected now to the positive side of our battery. We then use this resistor, which is connected here, to bridge across to this row here, where we come across, and if you look at the diagram, we connect the positive end of our battery along the resistor. Then we find the resistor is connected to the positive leg of our LED. And so we've connected the anode of our LED into this point here, which is now on that shared rail. And that goes across onto the next line here. The negative side of our LED is now connected to the negative side of our battery. Okay, so we use this wire along this path to connect the negative side of the LED to the negative rail here, where we've connected the negative side of the battery. But notice I can connect this anywhere along the path. It doesn't matter. As long as it's in that rail, that whole rail is now our negative point. Okay, so if we wanted to add another LED, we make sure we've got it the right way around. All we need to do is to add it in parallel. If we look at our schematic, is to add it so that the positive side of our second LED is connected to the positive side of our first LED here, so connected across the top, and the negative side of our second LED is connected to the negative side of our first. So all we need to do is connect the anodes and the cathodes along the same rail. So if I go ahead and shove that in there, you should see that that is now lit up, just because they're sharing the same thing. So those two LEDs are now in parallel with one another. Okay, and that is breadboarding basics. Now I just want to make a quick note here on short circuits and the diagrams I'm showing you. Now a short circuit is when the current flows outside of our intended circuit, right, with almost no resistance, and this is very, very dangerous. This can cause heat and fires, okay? So let's take this simple circuit that we've had where we connect the positive end to the resistor, through the resistor to the positive end of our LED, from the negative end of our LED to the negative end, right? And we have our conventional current flowing through this way. Now, if we add in a wire from the positive end of our battery to the negative end of our battery, as we know, current will always choose the path of least resistance. Therefore, it will not choose to go through the rest of our circuit. Here you can see it's all faded out. It'll instead skip it all out and go straight through this wire. Okay, it won't split. It will just choose to all go through this, and you will eliminate this. This will also potentially cause damage depending on the power supply you have. Another thing to note is if we take this circuit diagram here where we have this resistor in series to these LEDs in parallel, and then we have this again where we connect this in one resistor in series to two LEDs in parallel. And then finally this circuit, which might look very, very different to the first, but in fact these are all the same. Okay, all we need to do is follow the dots. Positive to resistor, end of resistor to one end of the LED, to another LED, and then the two negative ends join up to the negative end. Again, positive to resistor, resistor then splits to the two positive ends of the LEDs, they join together to the negative end. Positive, resistor, resistor to one positive end, resistor to other positive end, negative and negative. So this is all exactly the same. Okay, so you might just see different diagrams drawn differently. Now, if we take a look at this simple circuit that we were looking at before, where we have our resistor connected to our LED, connected to our ground, and that's it. Now, if I take a wire between the positive terminal here and the negative, all I have done there is connected the positive of the battery to the negative of the battery using this one cable. As you can see, the LED has gone out. If I disconnect it, the circuit is restored, and this wire is incredibly hot, I can tell you that now. We can get the same result by putting that positive into the negative. There, we can also get the same result. Now I urge you not to do this, please do not, because as that wire got very hot, indeed, these batteries can get very hot, and in some circumstances you won't get so lucky, you can short things and you can cause a lot of problems. Right, now switches. So we've already been breaking our circuit by just disconnecting the wire, as we did before. But we can now use switches to break the circuit instead, which are a lot less fiddly. And there are all types of them, as you can see here, little dot ones, push switches, toggle switches, slide switches, and they come with various sizes. They have one function. They make or break the circuit. They either prevent the flow of electrons or break the flow of electrons, okay? So here you can see, as we close the switch, the electrons are allowed to flow. We open the switch, the contact is broken. The circuit symbol literally shows a break in the circuit, okay? This is open and we want it closed. There are also different types of switches. There are push to make, which if you push down on here, if you imagine this is a contact here, if you push down on this, it will join these two contacts together and it will make it. And there are others where it's already joined, and if we pushed on it, it would break these components. So if we push down on it, it would break this, and so it would stop the connection. They just work oppositely. And here you can see we push down on it, it makes a connection, and it will jump back. Okay, so there are different types of switches. Okay, so introducing the switch. Here we have a little red push to make switch where we push down on the top, and we join the contacts here below, so these two terminals. Using a circuit that we have here, we're going to place these two terminals across here and here. So now if we play our game of connect the dots, all we need to do is follow the positive terminal of our battery. Along this rail, we have the yellow wire here connected between the positive and our switch, as we can see in our schematic on the bottom right. the other side of our switch then needs to connect to the resistor. So the other side of our switch connects to this rail, where we have our resistor connecting and joining it to the positive leg of our LED along this rail here. So they're sharing this rail, and therefore the positive end of our LED is connected to the resistor. Negative end of the resistor needs to connect back to our terminal. So we use this negative terminal, so we use this piece of wire to connect back to the negative side of our battery. So now, when we press this switch, we're going to join the contacts and we're going to create and complete the circuit. And so there you can see, as we press the switch, we light up the LED. Very simple. Okay, so what we're going to do now is we're going to start from our battery end. Okay, so we're going to take our positive terminal leg and we're going to connect it to our positive rail, our red one. I'm just going to use it for the simplicity. I'm going to connect our negative to our negative rail. Okay, so we have this connection here and we're going to connect it to our switch. Okay, so we're going to take our switch here, and it doesn't matter which way around this goes because it's just going to make or break, and we're planting it across this rail here and this rail here. Okay, so these two rails are connected to that. So to connect it, we're going to take a piece of wire, we're going to put that up from the positive end to one of those rails, to the what's going to be the positive end of our switch. So now we have it flowing through here, across here, and into our switch. We then take the other end of our switch, so this rail here, okay, which will only be joined together once we close down on the switch, and we're going to put that into this rail here. Okay, so this is now the other side where we're going to connect an LED, positive side into that same line with the resistor. Actually, let's make it this way around so it's easier to see. Okay, so we're going to connect positive side into here, negative side into this rail, and then finally we just need another piece of wire. We connect this side into our negative. We close the loop. Okay, so can we see we go from positive along the positive rail through this grey piece of wire into our switch, across our switch, into the next line, which we connect our resistor to. Okay, so we're connecting our resistor. Remember to look back at this circuit diagram. So we're connecting the other end of our resistor to the positive leg of our LED because they're on the same rail. And then we connect the other end of our LED across to the negative side of our battery. Okay, so now when we press down on the switch, we close those contacts together and we make the loop. We close the loop and our LED lights up. Very cool. Okay, trust me, things are going to heat up, but you need to understand the basics of circuits. Okay, so here we have diodes. Now, LEDs that we've already looked at, light emitting diodes, are a type of diode. Okay, and it's very similar circuit symbol. We just don't have the light emitting from them. And they only allow current to flow through one direction. Again, they have that polarity, so positive side and negative side, here anode, cathode. And the component has that highlighted by a small grey stripe, right? So current can only flow through this way. Okay, that small grey stripe is that almost line, if you want to think of it, that stops current flowing through. So here, a diode would cut off the circuit we made. So the current would be flowing through conventionally, going through, and bang, it can't go through our diode, okay? In this circuit here, when we have that short circuit, so let's say we connected a terminal across these two, if we now put a diode in that place, the current will want to flow through and it won't be able to go down this path because there's so much resistance, and all the current will flow normally through our circuit, okay? So you can think of a diode, if you want, as a kind of valve that only allows water to flow through one way. So here we have the water flowing through, fantastic, and here it reaches a blockade. This is opposite to this way. Sorry, the diagram's the wrong way around. Diodes can be very useful for preventing electricity from reaching sensitive components, or ones that we don't want to get damaged by current going through them. Okay, so here we have our diode, and with that little grey silver line there, just showing you which side is the negative side. And so if we take our circuit from before, all we've done is replaced the grey wire now with our diode, and we have the diode facing this way so that the positive side is on this side of the LED, where we've got the positive connection of conventional current. So now when we press the switch, it still works. But now if we turn the LED, diode around, so it's facing towards the LED, when we press the switch, nothing happens because it's stopping the flow of current in that direction. Okay, so next we have capacitors. Capacitors, in a very simple aspect, store electrical energy. They store energy, and the amount that they store is what we call capacitance, which is measured in farads. And here you can see kind of a variety of capacitors. So there's lots and lots of different types. And they can release all of that energy at once. Okay, so they can store it up and then release it, just like a camera flash, bang. And there's lots of types. The capacitance, however, is usually in a range from microfarads to picofarads, so very, very small. And some capacitors, such as this big one here, will have a polarity, such as like our diode, where they will have a positive and negative, so anode and a cathode. The negative side is shown by this grey stripe running down the side, and it will also have a shorter leg. The smaller ones, however, will not have a polarity, and you can put them around any which way you want. Now, these capacitors are great for filtering and smoothing of signals. In terms of a physics explanation, essentially contains two plates, hence the circuit symbol. And these two plates have a non-conducting material in between them, where essentially electrons move. So when we close the circuit here, all the electrons move from the one side to another side, and they can't get through. So there's a buildup of electrons, which creates this potential difference, and then those are released when it's not charging. So here we can see another circuit. It's firstly the switch closes this loop here, and we can see charging. There's build-up of charge, and then the switch turns to the other loop and lights up this LED. So the energy that was stored up when it's connected to the battery is then released through the LED. It's useful to think of a capacitor as a water tank that stores the water or the energy, and then when it's cut off, releases its supply. So if we look at the diagram on the bottom right, we can see that a first switch, so the bit highlighted in yellow, if we close that first switch on the left, we are going to charge up our capacitor. We're going to close the loop on this yellow part. The area in black on the right, because that switch is open, won't be connected. So we're going to charge up our capacitor. If we then open up this initial switch, our capacitor is still charged, and then when we close this second switch, all of that charge will then power our LED for a little time, very, very short. So to demonstrate this, I'm going to take a 9-volt battery, and I'm going to show you some of the capacitors ranging from rather small to a little bit bigger, to just a little bit larger. Now these two, note, have no polarity. You can put them around either way. This one, however, has a longer leg and a shorter leg, and the shorter leg also has this grey marking, this stripe down one side to let you know that this is your negative leg. So firstly, if I take this small little capacitor here and I put it across the two terminals of this battery, just as if I was closing that left switch, I can then take it away. I can then take in a LED, as we have here, and if I put it across the two terminals, you'll see a very, very brief light. I'm going to do that again. You'll see a very brief flash. Okay, you might have missed that because it's so dim. However, if I take this larger one and put it across the two terminals, making sure I put it the right way around this time. Don't need to leave it there for long, I'm just doing that for effect while I'm talking. And now I put this across my LED, you'll see a much larger flash, and see how quickly it loses that energy. It discharges very, very rapidly. But there you go. So DC motors next. Here you can see the circuit symbol for a DC motor is essentially very aptly just a circle with an M in it. And here you can see a standard DC motor. There are lots of great explanations as to how motors work and all of the science behind it, but that involves explaining a lot of stuff, and I'm not going to go through it here today. You can be sure there are some resources online for that if you want to find those. Very simply, DC motors rotate when current flows through them. Okay, so here we flow current through it and it rotates. Rotation, however, depends on the direction of current flow, and this is for DC motors. Okay, so if we now turn our supply the other way around, connect the positive end to this side of our motor, we're going to flow current through the other way, conventional current in this case, and our motor is going to turn the other way, right? So we can get clockwise and anti-clockwise rotation, which is very, very useful for going forwards and backwards. The speed of which is proportional. So if we stuck to voltage, so if we stuck a larger power supply here, we would drive more voltage through, forcing that motor to spin faster. Okay, two things that you kind of need to know is that motors themselves have a speed rating and a torque rating. Okay, so speed is in revolutions per second, and it's how fast it rotates. Okay, torque is how much force it generates. You can have something spinning really, really fast, but it doesn't have a lot of force behind it. Okay, and we'll demonstrate that in just a second. Generally, gears are introduced to a lot of motors to reduce the speed. So we reduce the speed and increase the torque, or vice versa. So here we have a small gear connected to a bigger gear, and here this one's spinning really a lot faster. This one's going to have more torque to it. And here you can see this motor has been shafted onto the end here, and throughout this whole yellow casing are lots of gears. Again, you see a similar motor size here. Lots of metal gearing connects to this shaft, creates a lot more torque. So this is harder to stop, but it spins a lot slower. So here we have a regular DC motor, and we've put it into a little yellow gearbox. So this is going to increase its torque, and this goes through to 2 axles. Now I've put a bit of black tape on this one here, just so that you can see the rotation more clearly. So now if we take a regular 3-volt battery pack that we've put in series here, and we connect our yellow side of our motor to the positive and our red side to the negative, like so, you'll see we have an anti-clockwise rotation. Now if I swap over the yellow now to the negative and the red now to the positive, you'll see we now have a clockwise rotation. Now, if I go ahead and get rid of that and get a higher voltage power supply, such as our PP3 9 volts, and I connect our yellow in like that, our red like that, you'll see we have a much faster rotation now. And if I swap the battery over, you'll see we now have that faster rotation, but in the other direction. And that is the very basics of DC motors. The potentiometer. Okay, so variable resistors. I do suggest looking at videos on potential divider circuits and understanding all the current and voltage happening, all the changes happening across them. However, they have a very, very simple circuit symbol. Here you have what looks like a resistor with an arrow that essentially slides across. And this is what a rotary potentiometer looks like. Okay, so this will spin and it will change the resistance. Okay, so it'll essentially change resistance depending on some means. Some are sliders, some are rotational, and some have electrical inputs. But here you can see the rotation changes that slider, changes how much resistance is going through. So what we can do is we can control the output voltage by turning this knob. Okay, so we can change how much voltage is flowing through, and we've got 3 legs, A, C, and B. So usually one side will be A, where you connect one side of your power supply, so this side here. C will be your negative or ground, and then B will be your middle leg, or your slider, which essentially is your output. So we turn the knob, and we vary the output voltage on what we call the wiper pin, which is the one that slides along, it wipes across, okay? And it has those 3 pins, the positive, the negative, and the wiper. So it's charged. Okay, so before we get into all of this nonsense right here, let's first have a brief discussion about the schematic on the bottom right. What we have here is our positive end of our battery connected to one terminal of our variable resistor. The other end of our variable resistor is connected to the ground of the battery, so we have this loop. Now, what we have here is our wiper pin, which is going to move up and down, and it's going to change the resistance on either side of our variable resistor. As the wiper increases on this side, goes up, the resistance on this lower side is going to increase. Okay, the increased resistance here means that we're going to get an increased voltage across this portion of our variable resistor. We've decided to put our motor in parallel with this side of our variable resistor. So as this increases and our R increases, our resistance increases, our voltage is going to increase because we have V equals IR. So V, the voltage will increase if R goes up as well, they're proportional. And because of this, we know that if our resistance and voltage increase here in parallel, our voltage is also going to increase through our motor. So as we twist the knob and change the resistance here, we're going to see an increase or a change in voltage across our motor. If we now turn to our schematic here, we see that we have the positive end of our battery connected to one terminal through this red cable of our potentiometer. The negative end here coming the opposite end connected to the ground of our battery, or the negative side of our battery. The wiper pin in the middle with this orange cable is connected to this row here. We then connected that row, so this wiper pin, to our motor via this yellow pin. So this is now in parallel here. And the other side of our motor connects to ground. Okay, so we've completed the schematic that we have on the bottom left. So now, if I gently take this and I adjust the knob, you can see that I can slow the motor down and I can increase the speed of the motor as well, just by turning this knob. So we're changing the voltage that's being allowed through to the motor. Okay. Right, so servos, we can think of, here you can see, right, so servos. Servos, instead of continuously turning like a motor, will turn to a set angle. So here in this little GIF, you can see the servo turning 0 degrees, -6 degrees, and positive. Okay, so it's just rotating. It's been programmed to do this, and it's just constantly looping. Now you can see a very small servo, a little bit bigger servo, and then a very, very large one. We tend to work with these two in hobby robotics. So you can program it to turn to a set angle. And you can think of a servo as a hybrid between a motor and a potentiometer. Essentially, the motor turns the shaft, causes that rotation, and the potentiometer reads its current position. So it reads how much it's rotated, converts that voltage into an angle, and tells what point it's at. Okay, so it uses these two components that you looked at before to figure out where it's at. Now a servo, this little component down here, has 3 pins. A positive pin, so some voltage going in, or current going in, sorry, and a ground. So we have to complete that loop, obviously. And it also has a control pin. Now this control pin decides what angle you want your servo to turn to, okay? But unfortunately we can't make a servo just turn using just a regular voltage. We have to actually use something called pulse width modulation, or PWM, okay, which is a clever technique of essentially turning on and off a signal very, very fast. So digital signals here, demonstrated here, are always on or off. They're either high or low, okay? So here we have a digital signal always on, and we break it down into these little time periods, these little periods here. And within this time period, it's always on. Within this time period, it's always on, and so forth. And because it's always on, our output is always 100%. It's always 5 volts, or it's always high across here. Here, between each one of these time periods, we're turning our signal off. We're turning our digital signal off. We're keeping it low. Okay, so the next time period, we keep it low. Next time period, we keep it low. So the output is always 0%, 0 volts. Okay, now within these time periods, we have an opportunity to switch on and then off our signal. And here we've kept our signal on for 25% of the time within this time period, and we've done it again and again and again. So therefore, output voltage will be 25% of, average output voltage will be 25% of our maximum, because it's never quite there. It's always off for a little bit of that signal. And here, the servo uses the duration of these pulses in these little time periods to tell what angle to turn to. Now, I'm not going to do a demonstration of the servo because you can see it working here, and I'd have to program it to a little board, and so you wouldn't really see a lot. So we're going to move on. Okay, transistors. The theory behind a transistor is insanely complicated if you want to go in depth, so I'm going to have to gloss over it quite quickly. Okay, but essentially here is a transistor, and this is what they look like. And again, varying types and sizes depending on their applications. Their basic functionality, if you want to think about it so easily, is that they operate like an electrically controlled switch. Okay, electricity at our base pin, which is labeled B here, controls the current flow through our collector to our emitter. Okay, so this pin here is like a switch that basically controls the current flow from our collector to our emitter. Okay, this will close that switch. You can also think of this like a valve or like a tap. The base pin controls the valve, and it controls the flow of current or water through from our C to our E. Okay, so if we take this circuit here that we have, and we've got the positive going through to our switch that's open and goes through to our LED. If we close this, the LED would light up. We can now replace our switch with our electronically controlled switch. So here we go positive into our collector, and then that would go through to our LED when we close this. Okay, so when we allow the current to flow through to the base pin, that will then in turn close the switch or the transistor and allow the current to flow through. Okay, so this is like an electronically controlled switch. So a transistor, if we apply a positive voltage across the base, so we're using the switch to turn on and off our base, the current will flow through. So here we've disconnected it, and here we've connected it. So here we can see we've got our switch closing, and we're lighting up that LED, or we're essentially closing the valve on our tap. Okay, and what we're doing is we're applying a positive voltage from our base, our current's flowing from our base to our emitter in conventional terms, okay, which allows the collector to emitter. Now, what I've shown you a little bit sneakily is an NPN transistor. Okay, this is one half of the story, but it's not all that complicated. This means that we have a positive current flowing from our base to our emitter, allows a positive current to go from our collector to our emitter. A PNP transistor, however, if you look here, the arrow is no longer pointing out, it's pointing into the base. That's because if we now have current flowing from our emitter to our base following that arrow, so we turn over our power supply here and we have PNP transistor, if we allow the current to now flow from our emitter to our base, like this, and we create this little circuit here, we now allow the current to flow from the emitter to the collector. Okay, so we allow this cycle now, right? And we light up our LED. So again, these essentially just work in an opposite manner. Okay, and what's important to know is now we have this difference in our direction of current through both of these transistors. Now, you might be thinking, why use these transistors? We've had to add in switches and stuff. Transistors basically make up kind of all the electronic appliances you have now, and they are used for two primary functions. Switching. Obviously, we don't normally put switches here. It's usually a digital signal that allows this to open and close very rapidly. So we can transmit a signal, and we can open and close a switch, allowing current to flow through. And we send this signal through with a computer or a digital system of some sort. The other thing we can do is amplify. So we can have a very small input signal, because the transistor doesn't need a lot at the base pin to allow current to flow through it. So we can put a very small signal through here of this, let's say this digital signal here, of maybe 3 volts. But we've got a power supply of 30 volts. Every time that this is high, every time that current flows through, it's on, this will close and create a high peak going through of 30 volts, which will basically increase the amplitude of our signal and amplify a higher voltage. Okay, so before we get into the circuit part, which is a little bit more complicated now, we have these two transistors. So here you can see a smaller one and a larger one with just different ratings, but both work in exactly the same way. So now if we go ahead and insert our transistor circuit like so, let's just break this down slowly. While there looks like there's a lot going on, it's not too complicated if we work through it. So here we have our initial battery supply starting from our left, and we connect the positive end of that to our switch. So what we've done is we've connected it here along this rail here, to our switch here. Okay, so along this rail, and the other side of our switch connects to the base of our transistor. So here we connected it along this rail, used an orange wire to bring it down to the middle pin of our transistor. The middle pin of this transistor, if you look up the data sheet, which we'll get onto at some other point, will be your base. So you can see that the middle one is our base. This one here is our collector. So this one at the top is our collector. And this rail here is connected to the positive side of our secondary power supply, our 9 volts in this case. The emitter side, this rail here, now connected to our emitter side, is connected through this yellow wire down to our motor, and the other side of the motor is connected to ground. So are both of the negative terminals of our battery supplies. Okay, so now if I get this in place, when I press down on the switch, I will close the circuit on the left, and I will force current through the transistor from the base to the emitter. Because this is an NPN transistor, this will allow the current to flow from the right side of the circuit, from the collector to the emitter. So here we can see, as I press down, I'm allowing that current to flow through. And that's it. Okay, so now I want you to think about running an application here. So what we're going to do is we're going to introduce the next part with a little bit of a challenge. Here we have our robot, which has 2 wheels, and we want our robot to move forwards and backwards. Okay, so we want our motors then to change direction. We want them to go forwards and then backwards, clockwise and anti-clockwise. Okay, very simply, we know from our knowledge of motors, DC motors that we've looked already, we can switch over the wires very, very simply. Here, if we have the positive side going to this side of the motor, we'll have it spin one way. And if we have the positive then switched over to the other side of the motor, it'll spin the other way. Therefore, we have our forwards and our backwards, right? So all we need to do is disconnect the wires and switch them over. However, that's not very practical if we want to be switching over the wires constantly here. It's rather fiddly. So what we do is we implement a very, very clever switch circuit, which is called a H-bridge. And here you can see, using these 4 switches, S1 to 4, if we close S1 and 4, the current is allowed to flow through this little zigzag all the way through, and we rotate our motor one way. If we then open those 2 switches and close the other 2, 2 and 3, we allow the current to flow through the opposite way, changing the motor direction. Very, very simple, right? And this allows us to kind of create a simpler structure. However, we're still chasing our robot around. Okay, we're still pushing down on these switches, having to hold 2 down at once. It's not a very sensible option. So we replace this switch circuit with transistors, which we can now send digital signals to and we control electronically. Okay, so here you can see the use of PNP and NPN transistors. To close the Q1 and Q4, we allow it to go through this way. To close Q3 and Q2, and we allow it to flow the other way, changing motor direction quite simply. Now, obviously, we need to control these switches with a processor, because we're not going to sit there and push down the switches to allow voltage to go through them or current to go through these. So we need to add a processor, and there'll be a little bit more on that later. But essentially here, we introduce current flowing through. We have our DC motor spin one way, have it go through the other way, and it'll spin the other. Right, so we've just looked at this H-bridge circuit with all the transistors in, and here you can see a circuit breadboard for that. Okay, so here we have our PNP transistors and our NPN, a little switch to tell the motor which way to turn. Now I could wire this up and we could go through it, but it's going to be a big jumble of wires, as you can see, and so it might take a lot of time. Instead though, this jumble of wires, I can tell you, can be more compactly found in what we call an integrated circuit, or an IC, which is essentially a chip like this. Okay, and this chip here houses all of this electronics. Okay, and it's a lot more compact, a lot smaller, it's a lot neater. Okay, so you can find all of this circuitry kept in a tiny unit, and there are all kinds of integrated circuits for all kinds of different functions. You could go on and on about it, and I know you've probably heard enough of me already today, so I'm not going to bore you with all that. You can look them up yourself. Essentially though, all that electronics in a tiny little chip like this, great, let's do that. Each integrated circuit has a code written on it, so when you're looking at these things, they all look exactly the same. You might not be able to tell. Some are bigger and some are smaller, depending on what they're used for. But essentially, to tell what it does, each IC will have a little code on the top here, written to tell you what it is. Google that code and search the data sheet. Okay, the data sheet is basically like a map of the pins. So here you can see we've just cropped out a little bit of the data sheet, and essentially all it does is it specifies what all of the legs on this integrated circuit connect to. So here you can see it for these two ICs, and we use this, and these will be a lot clearer on the actual data sheet as to what A and Y and such connect to. However, don't worry about that too much now. What you need to know about is you can just Google data sheets and it will tell you what any electronic component does. Okay, you just need to use that code on the top. Note, firstly though, main things, when we're looking at these integrated chips, you might not be able to tell which pin this is. Is it this one, this one, this one, this one? The way to tell is basically this little knob at the top is marked on all of your data sheet circuits, and it relates to this little dent in the top. Okay, so this is the very top of your integrated circuit, and we number our pins from left all the way down, 1 to 8, and then right all the way up. Again, left, down, right, up, and that's how we know which way around. We've got our integrated circuits, and we know that we're connecting the pins to the right thing. Now we're specifically looking at the H-bridge that we've already introduced before, and what this tiny little chip does is it has all those transistors and everything going on inside of it, so that we don't need to make a complicated breadboard of it. And here we have a top-down view. This one little chip will control 2 motors, and that's 1 per side. So let's just take a look at one motor. I'll blank all this out. Let's take a look at one side of this chip. Okay. The first pin, we need to connect this to 5 volts. Okay, this will enable that motor. So motor 1, this is controlling that motor 1. This will enable the motor to turn on. So this is our on-off switch essentially. Here, our pin 2 and pin 7 connect to our motor controller. Okay, so this is our processor. This is what sends the signals to our chip, telling it which way to turn. Motors 3 and 6 connect to our actual motors, so each leg of our motor, and 4 and 5 are connected to ground, so we connect those to 0 volts or our negative rail. And then finally, this pin here, 8, is the motor power, so we can apply a separate power supply to our motors, and obviously we know that if we increase the voltage, they're going to go faster. So when we look at these M1 forward and M1 reverse here, if we apply 0 volts across both M1 and M1 reverse, it's going to stop. Nothing's going to happen. If we apply 5 volts, so a difference here, and 0 volts across one, the motors are going to spin one way. If we then put 5 volts across this one and 0 volts across this one, we're going to go into reverse. And if we put 5 volts across both M1 pins, it's going to stop again. So this is how we control. We send a different voltage down each one of these rails, and it will spin a different direction. We also have a positive 5 here. This pin here just needs to be connected to 5 volts to turn on all of the logic. This powers all of the the chips and the transistors and everything going on inside. Okay, so this is just connected to 5 volts. Then these pins here all do exactly the same thing for the other motor. Okay, so here we have the H-bridge integrated circuit already wired up. As you can see, we've done one half of it, so we have one motor here. Just for this demo case, we won't bother with the other side. And as you can see, there's a lot less wiring involved and it's a lot more compact. Firstly, let's go through the pins just to make a sense of all of these wires. It might look daunting, but it's not actually that difficult. Our first pin, pin 1, is our motor 1 enable pin, which needs to have 5 volts sent to it to turn the motor on. We've decided to use this green wire along to pin 16, which also needs to be 5 volts for the logic. And we've hopped it along this green wire to our processor, which is outputting 5 volts along this green wire, which is then shared across here and further down as well, but we'll get to that. These white pins, which are our motor forward and reverse, so our actual connection signals, are connected to the processor. This is programmed to output 5 volts and 0 volts alternatingly between these two wires to make the motor reverse and go forward. So this is alternating all the time. Then we've connected pin 3 along this rail, so you see pin 3 across the rail, to the first pin of the motor. The second one comes out further along down here. The two middle pins are connected together because they are the ground pins, and the grounds on the other side are then connected to the ground on our processor. We haven't plugged it in just yet because we don't want the motors running around while I'm trying to talk. The other side of the motor is then connected here, and the other signal pin comes in. Finally, the motor power in pin down here is connected as well to the same 5 volts that is powering the chip and enabling the motor. So we're just sharing that 5 volts across. Okay. So as you know, it's just a simple follow the dots. So now if I connect this to our ground, you can see that these signals are alternating and therefore driving the motor forwards and backwards. And you can see that with the black tape. And that is a very, very simple integrated circuit. Okay, so there are lots of types of sensors that you can use and look at if you want to get interested. I'm just going to cover a few here that we're going to usually use in some hobby and low-level electronics. Firstly, we have the LDR or light-dependent resistor. Okay, this changes resistance with light, as the name so aptly suggests. Essentially, it looks like this small little component here, and it essentially looks like a resistor with a circle around it and 2 arrows facing in this time, which is opposite of the light emitting diode. Okay, and essentially here you have the current is going across here and it's blocked. Then you apply light, that reduces the resistance and the current is allowed to flow through. Okay, we decrease the resistance and the current flows through. Our second sensor is the ultrasonic sensor here, which looks like these googly eyes, and the circuit symbol also looks like a pair of googly eyes. The ultrasonic sensor uses echolocation, if you want to think of it, to calculate distance. Okay, so it transmits a signal, bounces off the object into the receiver, and it uses the time taken. So it emits and then it listens, uses the time taken for that response to get back to calculate the distance of that object. Okay. LiDAR, in a very similar manner, emits a laser instead. So it uses light of a different wavelength to visible light to calculate the distance based on time instead. So here we have the image of a LiDAR. So you've got the emitter and then the receiver. And this is more accurate as it uses light and not sound. So to understand this circuit, first we need to fully understand how an LDR reacts to light. So an LDR's resistance decreases with light intensity. So in a fairly dark environment like now, it's going to be quite bright. This is because as we increase the light to the LDR, its resistance is going to decrease, and so will its voltage. Now, with our LED in parallel, the voltage will be equal to the LDRs. So as we increase the light, decrease the resistance, and decrease the voltage, The LED will also reduce voltage and then again dim. So let's plug this in, and we see that in this dark environment it's fairly bright. Now as I bring over my lamp of my light over my phone over, you'll see that the LED turns off there. So as light intensity is high, the LED turns off and on. So there we go. So I'm moving the light away, it's dark again. I bring the light over to the LDR and the LED turns off. Okay. Okay, and finally we come to the most complicated of all the components, and there's lots going on in here, there's lots of chips and everything. But essentially, this is the brains of our operation. This is the brains of lots of our projects, and you'll come to be familiar with it. There are various sizes of these, but we usually work with the Uno, which is this size here. It's the Uno. Digital input-output pins. Okay, so these ones down here, 0 to 13, are digital input-output. So they will emit a high or a low, as 5 volts or a 0 volts. They're on or off. That's what digital means. And they're input or output, so we can read what's coming in on them, tell if it's high or low, or we can emit 5 volts or 0 volts. It also has 6 analog inputs down here, A0 to A5, and various 3 volt, 5 volts, grounds, voltage in, and grounds here, various other pins that we can use to power projects. Pins now with these little squiggly lines here are select pins that are also capable of pulse width modulation, which is what we were talking about before, where we can vary the time of these on pulses to emit a voltage which is not just 5 volts or 0 volts, but somewhere in between. Essentially what we do is we program this, so we control and we tell it what to do, to read inputs and transmit specific outputs. Okay, there'll be more of this during the following weeks, and this will make a lot more sense. Okay, so next session we will be doing a live session on Tinkercad. We'll be building all of these circuits and testing them yourself virtually, and we'll be experimenting with a little bit of Arduino if we have time. I am sorry that this has been such a long and arduous session, but it is going to be very, very important for you guys in the long run, understanding the basics of this. So thank you very much for listening, and we'll see you on Thursday.